we're going to look at how to work with polar coordinates and rectangular coordinates, as well as just working with polar graphs. So this says find the polar coordinates of this point. Now this is actually a rectangular point. It's technically just an x and a y, like the good old days. And let me even graph this point. There are some formulas out there, but really just drawing it is the best. When in doubt, draw it out. And for this, you graph the horizontal component, which is the x in the x-axis. So it goes over 2 root 3, which, whatever number that is, that's just this distance, 2 root 3. And then, of course, I'm going to do the vertical component, which is the y direction, the y coordinate, and it's going to go up 2. And so there we go. And so here, actually, here's our point. Let me just draw a big dot there. That's our point based on these rectangular coordinates. Notice it kind of, goes in rectangular directions like base and height. But we actually want to convert this into a polar coordinate, which is actually an r and a theta. It's more like angles and hypotenuse, as you'll see. The r is sort of the radius out, and the angle that got us there. Of course, the angle that got us there is this angle right here from standard position. Okay, so if I draw that triangle a little larger from the quadrant 1 triangle, we have a horizontal component of 2 root 3 and a vertical component of 2, but we want the angle that got us there and the radius out to this point, which is r. So to do that, we basically just do Pythagorean theorem, and that's the formula for finding r. r is actually the square root of the x square plus the y square. Remember, usually r is square, but like if I wrote the full Pythagorean theorem out, it would look more like this. But of course, we want to square root both sides to get r by itself. So it's that it's r equals instead of r square equals. So we would square root and square root. So that's how we get this version of the formula. Really, it's just Pythagorean theorem. So let's crunch this. Let's see, what's the x? The x is the 2 square root of 3 squared, plus the y is just the 2 squared. We're going to square root all of that. And so our r will equal, well, of course, it's going to be a giant square root. This one's easier, so let's jump to this. 2 times 2 is 4. Okay, there's that. Plus, now this one, it's 2 times 2 and a root 3 times root 3. So 2 times 2 is 4, but that's multiplied, because this is multiply, with a root 3 times root 3, which is actually normal 3. So here we go. So our r is actually the square root of 12 plus 4, which is conveniently the square root of 16, because that's just regular 4. So there's our radius. The radius for this, the hypotenuse, would just be 4. Check this out. This is a 1, 2, square root 3. It's actually just an enlarged version of a good old 1, 2, square root 3. Maybe you recognize that. Maybe you didn't. It's okay if you didn't. I won't hold it against you. So we found our radius. That's going to go into our point, our final answer. We also need the angle. Well, how do you find the angle? There's a formula for that. Let me make a little more room off to the right side. The formula for the angle is theta equals the tangent inverse of y over x. And here's why. Just look at the picture. I need an angle, and even before I found the radius, I could find the angle by doing opposite over adjacent. That's tangent. I need the tangent inverse. Opposite over adjacent. That's the y direction over the x direction. And I got to do the inverse to find the angle. So let's just use that formula, or use our triangle, really. And so what? The y was the 2 over the x was the 2 root 3. Okay. So we could use Desmos for this. In fact, I might even use Desmos in just a second, just to show that it'll give us the answer. But first thing I want to do is maybe I could simplify it. 2's cancel. But of course, there's an invisible times by 1 there. So it's really just 1 over root 3. Oh yeah, that's because this is really just opposite over adjacent from my basic triangle right there, my famous triangle. And you know what? You should know what that angle is, but watch, just in case you forgot. Let's go here. And let's just do the tangent inverse. So I got this pulled open. Tangent inverse, bloop, of the fraction 1 over the square root of 3. And of course, don't forget, I'm already in degrees. Let me check. I'm in degrees. And it gave me the angle that I should have known. I should recognize. That's just 30 degrees. Yeah, that's because This angle is just a famous 30-degree triangle right there. This is 30 degrees right here. We should have known that in the good old 1, 2, square root 3. So we've got everything we need. In fact, actually, now that we got the 30 degrees, that makes sense. Quadrant 1 is 30 degrees. So we can write our final answer. Our polar coordinate is the radius we got was 4. That's the hypotenuse. And the angle, which is the angle for this triangle, was 30 degrees. There is our polar point. But they said to put it in radians. So let's make this angle, let's turn it into radians. 30 degrees, we should know what that is without having to do any conversion formula. That is actually just a 4 comma pi over 6 in radians. So there we go. There's our official answer for this problem. Let's try another one. All right, find the polar coordinates of this. Again, this is actually the rectangular coordinates. This is the x and the y. Okay, and just to draw the picture of it, it always helps. The x is 0, so we don't go in the left or right direction, in the horizontal direction. We just go down in the vertical direction, the y direction, so it's like down here at 1. Okay, so there's my point. There's the point of the graph. Now we got to turn this into an r and a theta. That's our polar coordinate. Well, let's just use the formula. So r equals the square root of the x square plus the y square. Oh yeah, Pythagorean theorem. Although wait, like where's even my triangle here? It's technically just like, you know, a squished triangle straight down here. Oh well, let's use the formula. So it's the square root of the x is right there. That's 0 square, plus the y is right there. It's just -1. I'll make sure you use parentheses there, square. All right, so that's just the square root of 0 plus -1 times -1 is actually +1. And so that's just the square root of 1, which is just 1. Okay, the radius is 1. As I prepare my answer, it's just 1 comma whatever I get for the angle. Let's use our angle formula. Remember, the angle formula is the tangent inverse of y over x. And so plugging in the, plugging in the numbers that we get, the numbers they gave us, the y is -1 over the 0 is the x. Oh, wait. -1 over 0? 0 on bottom is bad. Oh well, you know what? Let's use Desmos. Let's see what Desmos says. If we go to Desmos for my tangent inverse. Oh, you know what? I already pulled it up. Let's just change this. It's actually just -1 over 0. Oh, -90? Now Desmos gave me the answer, but like a TI-84 calculator would not give you the answer because you can't divide by 0. 0 on bottom is bad. That's undefined. It would say domain error. You can't plug in undefined into tangent, but it knows that it's -90 degrees here in Desmos. Ooh, Desmos is clever. You clever Desmos, you. So it's actually negative, well, it says it's -90. Let's double check the picture. Oh yeah, we could just go 90 degrees. It actually squishes my triangle, and there we go. Oh yeah, and notice this. Like when you squish the triangle, it squishes the adjacent, but the opposite and the hypotenuse squish to become one and the same. That's why this is the radius of 1. Remember, it's not going to be -1 even though it's down. The radius just always shoots out like in all directions. All directions, the radius just shoots out. It's never negative. And so that makes sense. The radius is 1 and the angle is -90 degrees. So I could put that. I could also put positive 270. Comma positive 270. It's the same thing, but wait a minute. I'm supposed to do this in radians. So what would that be? So in radians, we would have the answer as 1 comma negative. Instead of 90 degrees, remember that's pi over 2. Or if we wanted to do like the positive version, like 270 degrees, it would be 1 comma, what is that, 3 pi over 2? Remember your quadrantal angles. So I don't know, maybe this would be the best one. And there's our answer as a polar coordinate in radian degrees. Now this tells us to convert that point to a rectangular coordinate. Now they didn't tell us, but really what they should say is convert this polar coordinate into rectangular coordinates. So this must be the r and the theta. And we got to convert it into an x and a y. So it looks like the radius is -2 and the angle is 5 pi over 3. That's just what they gave us. So if I draw this picture, we got, let's see. Whenever I graph something in polar, I know it's r and theta, but I always do the angle first. I got to know what direction I'm going. 5 pi over 3. Okay, hold on. That's not quite 6 pi over 3, which would be a full 2 pi, right? 6 pi over 3. It looks like it's pi over 3 shy from a full 2 pi, or 6 pi over 3. So it must be like in this quadrant. In fact, it's pi over 3 shy, and pi over 3 is 60 degrees. So let me get rid of this. We actually have a pi over 3 in here, which I'm thinking in the world of degrees is 60 degrees. Okay, so this is technically like a 60 degree in quadrant 4. So I'm just going to write that 60 degrees down there. In fact, I could even say it's -60 degrees. It's just right down there, negative pi over 3 down. All right, so I got that. Now I'm ready to do my radius, and the radius is -2. Wait a minute. Okay, so I go all the way around here, but then I do a negative radius. That means I actually don't go out in the positive direction. I actually shoot backwards in the negative direction, the opposite direction. So it's actually going to be in quadrant 2. Let me kind of erase like some of this. In fact, let me erase this because it doesn't go that way. It shoots that way, -2. Okay, so which means like this hypotenuse is 2. I mean, I could put -2 there, but it just means it shot that way. And it's actually, even if it was shooting positive direction, it'd go quadrant 4, but it's shooting the other way. But the reason why I drew quadrant 4 again is because I noticed that this angle here, the pi over 3, is actually the same or vertical angle over here. So this is also pi over 3, which again is 60 degrees. So I know this 60-degree triangle. 60-degree triangle is a 1, 2 square root 3. I don't even have to do fancy math for that. Now, if I had to do fancy math for that, let's just say you didn't notice that. Okay, that was very clever. But if I didn't notice that, there's actually a way to solve for the x piece and the y piece. So we could use the formula, or we can use the picture. The x piece is actually going to be r times the cosine of theta. And you can see it here, because this is adjacent over hypotenuse, that would be a cosine problem. That would be the cosine of my angle, which is pi over 3, would equal the adjacent over hypotenuse, that'd be x over -2. But I just got to multiply both sides by -2 to get x by itself. And so yes, you get r times the cosine of theta. So using the numbers like I did here, or using my formula, it'd be -2 times the cosine of, in fact, I don't have to use the simplified version. In fact, I should just straight up use the formula they gave me, the 5 pi over 3 they gave me. Watch this. This will actually make sense once I crunch it and I look at my picture. I drew the picture right away because I love the picture. It tells you everything. But I'm just going to use that one, and let's go to Desmos and type that in and see what's up. Oh, I'm in radians now. This problem is in radians. So that means I need to switch my Desmos actually into radians. All right, what am I going to crunch? I'm going to crunch this right here. Let's get it in my screen a little bit better. There we go. So I'm going to crunch -2 times the cosine of the fraction 5 pi over 3. And that answer is -1. Okay, what did I find? Oh, I just found the x value. That's the x. Yeah, so let me label that, actually. That x is just -1. And like I mentioned earlier, this, if you know your triangles, 60 degrees, this is a 1, 2 square root 3. There's the 2. Oh, but wait, this should be negative because it's to the left. It's actually in quadrant 2. Because this angle bumped us actually all the way around, but backwards, it actually gave me the right value with this negative angle, this negative radius, and this large angle. It made sense in the picture. That's to the left 1. Okay, now let's try the formula for y. Y actually equals r sine of theta. And that should make sense here, because if I just look at my picture to solve it, I would do a sine problem for this triangle, even pi over 4, or I could use the 5 pi over 3. But it's opposite over hypotenuse. That would be like y over the negative 2. And like before, I get the y by itself by multiplying both sides by negative 2. And so my equation is just y equals the radius times the sine of the angle. And let's not use this second quadrant angle. Let's actually use the full-on angle they gave me. So let's just use the raw values, the r and the theta from our problem. Negative 2 times the sine of 5 pi over 3. Like totally ignoring my picture, my triangle. Let's just crunch that in Desmos. Desmos. There we go. Okay. Let's see what we got. Oh, it's almost the same as what I typed in earlier, only this time it's negative 2 times the sine of 5 pi over 3. And this gives me, well, what is that, 1.73? What? Oh, wait a minute. Remember, this was a 1, 2 square root of 3. Let's try the square root of 3. Yes. 1.73205008. Yes, that's the square root of 3. And notice Desmos even told me it's positive. Even with the negative there, and even with just it's because of the big angle and it knows, this formula knew it should be in quadrant 2, and that should be a positive square root of 3. So this is positive root 3. Okay, wait. What are we doing? Yes, we are turning this polar coordinate into rectangular coordinates. We turned the r and theta that we drew here into x's and y's. The x is this piece, the horizontal piece, and the y is the vertical piece. It's the adjacent of my triangle and the opposite of my triangle. So our final answer is negative 1, comma, square root of 3. There are my, that is my rectangular coordinates. Let's try another one. Okay. All right. This is the r and the theta. Let's turn it into the x and the y. I'm just going to straight use the formula and then maybe draw the picture if things get crazier, just to confirm it makes sense. Okay, we know r is 1, and we know theta is 7 pi over 4. Whatever the heck that is. Whatever quadrant, whatever. Let's use our formula. Okay, x was going to be r times the cosine of theta, and y was going to be r times the sine of theta. So r is 1, well, that's easy. Cosine of 7 pi over 4, maybe not so easy. Let's go to Desmos. Of course, it actually should be kind of easy if you draw the picture. Let's try this though. Okay, this Desmos is in radians. Let's scoot that out of the way. Okay, so I'm doing 1 times, I didn't need it times by 1, but you know, I'm just plugging it straight into the formula without really thinking much. Pi over 4. Okay, what the heck is that? That's a crazy number. Wait a minute. Pi over 4 is a 45-degree triangle, like a 1 square root 2. I'm wondering what the square root of 2 is. Oh, it's not quite that, but wait a minute. 1 over the square root of 2? What if we make this a fraction and go 1 over? Okay, it didn't put that on the bottom, but let's make it on the bottom. 1 over the square root of 2. Aha! That was just 1 over the square root of 2. Okay, so that means this first part, this is just 1 over the square root of 2. Which could be my x value, but if you remember, traditionally, we don't like a square root on the bottom of a fraction. We don't like an irrational number on the denominator, so we rationalize the denominator. We times top and bottom by root 2. So then we get square root of 2 over 2. Root 2 times root 2 is regular 2. Okay, is that any better than this? I guess so. Then we can do the same thing for our y value. So remember, y is equal to r sine of theta, so just plug it in. 1 times the sine of 7 pi over 4. Of course, if I go to Desmos, while I'm doing that, I mean, wait a minute, sine of 45-degree thingy, just like cosine. Okay, hold on. Let's just type it in. Let's just type it in. There it is. All right, so 1 times the sine of this thing is negative 0.707. Remember, that's 1 over square root of 2. This is just the negative version. Interesting. Let's jot that down. Y equals the negative 1 over square root of 2. Of course, we should rationalize, and we know what the answer is going to be, just like the other guy. So it's actually going to be negative square root of 2 over 2. Okay, well, so there's my answer. My answer is square root of 2 over 2, negative square root of 2 over 2. And let's just think about why and how all that works, why that makes sense. Okay, let's go back to the original polar. We're going to do this angle, which, wait a minute, if you realize that 7 pi over 4 is a pretty big angle. That's almost 8 pi over 4. And 8 pi over 4 would be a full rotation, a full 2 pi. But we're actually a little bit shy from a full 2 pi. We actually only get to like there. We're actually pi over 4 shy. And pi over 4 shy is actually a 45-degree triangle. And it would be right here in quadrant 4. In fact, a 45-degree triangle, that makes sense. This is a 1, 1 square root of 2. In fact, it makes sense. It's actually a positive 1 to the right and a negative 1 to the down for our x and y direction. Okay? Oh, but wait a minute. Hold on. Our radius was not a radius of square root of 2. Okay, but it is this kind of triangle. Let me erase those numbers. That would be my nice, beautiful, like famous 1, 1 square root of 2. This one actually has a radius of 1. And so we have to shrink this down by dividing by root 2. Square root of 2 divided by root 2 is 1. So I got to divide this by root 2, which should be negative 1 over root 2. Oh yeah, that's our original version of the y value before we rationalized. And this would also be 1 divided by the root 2 to shrink it down, which is exactly our sort of non-rationalized denominator version. So it all makes sense. In fact, there we go. This is actually in quadrant 4. We have our rectangular coordinates. You can just use the formula or draw the picture. Okay, here are some polar equations and graphs. We're supposed to match them. Okay, if you have a calculator like Desmos can actually graph these for us. This should feel like cheating because it kind of is. But if I don't think it really matters right now for these if it's radians or degrees. Actually, I am in radians, so let's see. Watch, if I just go, I'll graph the first one over there. R equals 3 times the sine of theta. It's theta, and there we go. And it actually graphed it over here. I don't need quite so much calculator space there. And there it is. It's actually just a circle. Looks like it's got a radius of 1, 2, 3. Yep, because 1, 2, 3, 4, 5. That's a radius of 3. And the circle's going up. Which one is that more like? Looks like it's like this guy here. I've just matched it. Now, why does that make sense? It actually should make sense in terms of the graph of just sine. Sine is from the unit circle. And as we go through all the different values of theta, it just cycles through all the values of sine. Starting at 0, sine of 0 is 0, and going all the way up, through 90 degrees and 180 and any angle, all the way around a full 360. And it goes, all the way up to a value of 1 and down to a value of 0 and down to a value of negative 1, if you can think of the graph of, the graph of sine. And the graph of sine normally as an input-output would look like this. And go up and down, and keep repeating across. Of course, it also goes backwards. But this is a graph on like an XY graph, not an R theta graph. So for an R theta graph, it makes sense that as sine cycles from 0 to 1 to 0 to negative 1 and up and down and all that, it's just actually completing a full cycle of the unit circle, but it's 3 times bigger. That's why the radius, or this distance rather, goes from 0 all the way up to 3. Now, it does a circle here, Notice the circle starts at 0, and as each angle increases, the radius increases to its maximum amount, stretched out 3, and then it decreases. And then instead of going down here and graphing angles down here, the angles are now, or the radius is now negative, so it throws it back over there and it actually overlaps. So it actually, if you saw it graph, it actually graphed a circle twice, because as it goes around a full 360 as an input for angles, the angles that are down here in quadrant 4 get thrown back to quadrant 2 because of negative radii. If that didn't make sense, just Desmos told me the answer. Now we can check out another one. Another one that looks similar like that is this. This is almost the same as this other circle, only this time it's created from the unit circle of cosine. And cosine, if you remember when we start with cosine, cosine of 0, if we were to graph it on a normal input-output from the unit circle, cosine of 0 starts at 1, its highest value. Then it goes to 0 and then down to -1 and then to 0 and up to +1 and so on. It keeps repeating that. Same thing in this direction. Keeps repeating that cycle. But of course this is amplified by 3. Notice its initial angle at 0, or I should say its initial output with an angle of 0 is at its highest point, which this is multiplied by 3. That's why an angle of 0 here is going to get multiplied out to its highest point or farthest radius of 3. It's actually going to be this one. Bloop. And I can confirm that by, graphing the polar version of this in Desmos. So let's pull that back up again. Okay. If I graph and switch this to cosine, there we go. We see it's the circle and its radius is 3, shooting out to the right now instead of to the up like the other one. Okay. Now, since I got cosine pulled up here, let's actually type this one in. What happens if I times this angle by 2? It's like sped up with the old cosine, graphs. If it's 2 times, pew. Notice it actually sort of speeds up the circle and throws it around different directions and turns it technically into like a rose. And it's a 4-petal rose when it's twice as fast in there. When it's a 2 in there, oh, and there we go. We've got a match. The cosine with that 2 in there matches this one. I wonder what this one is. Notice this one is the sine and it's 3 times the amount. So if we pull up Desmos, and notice it changed to sine instead of cosine. We'll play with that here in just a second. But let's do it like it says. 3 times the sine of, not 2 theta, that's this guy. That was similar to this guy. We'll compare them in a sec. Let's go 3. Yeah, that's it. Notice a multiplier of 3 in there for the angle actually makes 3 petals. Okay, so we found the match. Just for the sake of it, what if I actually put this as cosine? Notice it's a whole lot like this guy. It is a 3-petal rose. It's just starting at angle 0, starts out at its farthest, distance in the petal, as opposed to the sine version with the angle of 0. It's actually sucked back into the smallest value, which is right here at the origin. Okay, so all the sine and cosine switches is where it sort of starts. Cosine starts farthest out, like a good old cosine value starts at its highest output, whereas sine starts at the smallest value. All right, well, enough of that. Let's actually finish this by graphing this. Now they set up this beautiful table. Well, I guess it's not so beautiful. We could plug all these thetas in, all these angles in, and calculate the output, which would be the radius, a different radius for each of these. It's going to be horrible and messy. Nobody graphs these by hand like that. Let's just fire up Desmos, and let's see what this looks like. First off, it's not going to be a perfect circle. It's got that amplifier in there. Remember, we just dealt with some of that amplifier stuff. Let's go 4 times the sine of 5. Since it's a sine, as we just talked about, it's not going to start out here at its farthest distance with an angle of 0. It's going to start sucked in at the center. Since it's a 5, a multiplier of 5 in there is actually going to be 5 petals. Okay, and notice the one that stands out the most to me is this one here at the 90 degrees at its farthest distance. And then, of course, it's got 5 petals. They look like they're evenly spread out. I could even show you that a full rotation, 360 degrees, chopped into 5 pieces. Of course, I'm just thinking in terms of degrees, even though technically I think I'm still in radians, but just this full cycle, starting maybe even up here, not even in standard position, starting here, chopping it to 1, 2, 3, for 5 little pedals or 5 little rotations, it's about 72 degrees each between these. I'm just using that to help me sort of estimate as I draw this. Okay, notice the distance out. The farthest it goes is 4. This radius is an awkward 4 crooked. So I'm going to do my best to kind of just sketch this. These are not easy to graph, and so I'll just do my best. So 1, 2, 3, 4. That was that, and it kind of had like, you know, whoop-ch, and then this pedal, whoop-ch. Now, if you remember, the other one wasn't a full 90 degrees down here. It was actually 72. So we can kind of think of where it's going to be at. 72 is, okay, so let me just see. This is 45-degree angle. This would be, we've got this chopped in 1, 2, 3, 4, 5, 6. Okay, so it's kind of chopped into these awkward spaces. I'm trying to just estimate as to what I think it would be. This 45 degrees looks like, yeah, because that's 45, isn't it? Yeah. Looks like they chopped 45 into 3 pieces. 15, 15, and 15. So 15 from 90, right? 75. So it would be, you know, a little less than that because we said it was 72 degrees. So somewhere around here, yeah. If you didn't understand all that, I'm just trying to do my best to get it in the right spot. 72 degrees, zoop, zoop, not quite 90 degrees, and not quite zoop, 75 degrees, a little less. In fact, same thing this way. This would be 90 going all the way to here. This would be 75, but it's not. It was 72 degrees, and so it would be like what, right here? Am I on the right? Yeah, I think so. And of course the pedal. And then the other ones, you know what? I'm just gonna try and like eyeball it here. Somewhere out here, and then somewhere out here-ish. Oh, wait, did I make it out to the right? No, I gotta get out to ring 4. So 1, 2, 3, 4. Yeah, there we go. These bottom ones got a little weird. But hey, that's not too bad. Okay, don't judge. Like yours is any better. All right, there we go. We graphed it. Notice Desmos helped us and just some key ideas about angles and radius and all that.